So the topic for today is going to be um, distribution testing. This is actually a fairly active and exciting area in sublinear algorithms that has seen a lot of work over the past, the past 3-4 years. So obviously, I don't think I'm going to do justice to the entire field. But what I'd like to do is to talk about one of the seminal results in this area, known as uniformity testing. And I think this will segue well with our previous discussion of balls and bins and show you a very compelling application of a balls and bins analysis. So, what is the problem? The problem is given, I'll say, sample access to a categorical, which is simply basically just a discrete distribution with support n, determine, so I'll refer to this as script D, determine properties of script D faster than learning script D. Now, of course, we need to understand what it means to learn a distribution, before we can make this more formal. And so the model that we will have, the model is that the algorithm gets S independent samples from D. The algorithm knows N, the support size. We'll see that basically the algorithm only needs to have an upper bound on the support size, and we say the support is the set of positive integers up to n, but that's not necessarily that's not going to be fundamental. Like the support can be essentially any set, and the algorithm doesn't need to know what the support is, although it will need to know a bound on the support size. So the algorithm knows the support size. The algorithm gets S independent samples from D and processes these to approximately determine a property of D with high probability. So this is the setting, right? So one way to think of it is there is some unknown distribution. There's an unknown distribution that we refer to as script D. An algorithm requests S independent samples from this distribution. The algorithm knows the support size, and it processes these to approximately determine some property of D. And I will explain what I mean by some property of D. We'll take some simple examples. So given that these are categorical distributions with a support, we will use vectors P, Q, etc. to denote the probabilities of a distribution. Somewhat abusing notation, I will actually just refer to P and Q as distributions themselves. So we'll sort of get rid of the script d, and we will just use the vector of probabilities to denote the distribution. So for any I in the support, I'll say P of I is just the probability of the element I, and P of S is going to be the summation of I and S of P of I. Right? This is the total mass on some set. Now, before I can formalize what I mean over here, which is what does it mean to approximately determine a property, let me first talk of a notion of distance between distributions. So one of the classic notions of distance is called the total variation distance. So this is, often referred to as total variation. Formally, this is defined as, I'm sorry, there's no sum, a max over any subset of the support of P of S minus Q of S. Now, if the support was infinite, then you would replace the max with a supremum. We are only dealing with discrete objects here, so I've just written a max. So given that we're dealing with a discrete universe or a discrete support, a discrete finite support, we can instead look at the L1 distance, right, which is just the summation of the absolute value of Pi minus Qi, where I is in the support, and this is actually 2 times the total variation distance, and that's an exercise. And so in distribution testing, typically many notions of distance can be used, but one often starts with total variation distance, which can be written in terms of L1 distance, which is often convenient to use. So one uses the L1 distance. Note that there, of course, are other norms that you can use. You can use any LP norm, and you can use, P is unfortunately overloaded here, so I'll say any LR norm, and you get you can look at which would be the summation of I in N of P of I minus Q of I to the R, and the entire thing to the 1 over R power. And a significant amount of the work, and there's also KL divergence, which is a different notion of distance. It's it's not exactly a norm, but and there are other notions of distance one can use, and often the relationships between these distances form a fundamental part of the analysis in distribution testing. But for now, what is going to be important for us is that for R less than S, we get that the LR distance is going to be more, at least the LS distance. So the focus typically is going to be on total variation, as I said, but we will see other norms appear in the analysis. So now the sort of the meta question in distribution testing, the distribution testing, I'd say, framework is, given a property, so I'll use bold P to denote a property of distribution. So what is a property of distributions? this is simply some family of distribution. So this is sort of the most general way in which this problem is stated. So given a family of distributions, which is also referred to as a property of distributions, and sample access to an input distribution P. So this is the distribution that we're trying to study. So we get sample access to this. I say this, and given a proximity parameter, which is called epsilon. So the distribution testing framework says you have a property of distributions, that's some family of distributions. You have sample access to a single input distribution. And so the algorithm is also given a proximity parameter epsilon. So the algorithm must have the following guarantees. If the distribution actually has the property or is in the property, it must accept with probability at least 2/3. And if the distance, however we measure it, of P to the property. Okay, what does this mean? This means I'm looking at the infimum over all distributions that have Q of whatever notion of distance I have between P and Q. And often what we do is specifically we will often just use total variation or L1 distance. So what this distance means is this is the minimum change in P to get to the property. This means this is the minimum amount of change in the distribution that is required so that it will have the property P. So one way to think of this pictorially is this is the universe of all distributions, the universe of all distributions over R support size. This is the set of distributions P. Now given any distribution, it could either be inside or outside. What we're saying is distinguish whether it's inside versus it being sufficiently far outside. So there's going to be this sort of gray region in the middle. So we just need to distinguish here to here. So I said if the distance, and so the distance you can think of as the amount of change required to get into the property. If this distance is at least epsilon, reject with probability at least 2/3. And these are the only guarantees that I require. So just to make this, to sort of cement this, if the distance from P this is less than equal to epsilon and greater than 0, do anything. So if you have a property that is sort of fairly close to, if you have a distribution that is fairly close to having the property, you're allowed to say yes, accept, or reject. But if your distribution has the property, the algorithm must accept with high probability. If it is sufficiently far from having the property, which means that the distance is more than epsilon, where the distance we will measure in terms of the infimum of the total variation, and I use the infimum here because this is an infinite set. And if the distance is sufficiently far, which is at least epsilon, then we must reject with high probability. Right? And this is the framework, right? So this isn't a specific question. I've given you a framework of questions. And a lot of this language is, of course, the language of property testing, stated for the setting of distributions. So any questions here? Any questions? Okay. And given this sort of overarching framework, actually the most basic. Technically, well, you wouldn't say subset of Rn, but it's a subset of distributions which are sort of vectors in non-negative vectors in Rn whose sum is 1, whose L1 norm is 1, right? So, but yeah, in general, you can state this for any set. Of course, there may be sets for which you don't have any algorithm. You don't have efficient algorithms. Well, let's talk about that shortly. What do I mean by? I have to tell you what I mean by efficient, then what all these things mean. But yes, for now you could think of P as just some arbitrary set. Of course, we were going to ask this question for very specific, interesting sets. And sort of taking this further, of course, the most basic question is P is a singleton. So, is a singleton, which we will refer to as the distribution X. So it's an unfortunate choice of notation on my part. So actually, no, sorry. I'm always thinking of P as the input. So, sorry, that is small p as the input. So let's say that the property is just a singleton distribution X. So this is a known distribution. It's an unfortunate mix of notation on my part that X is going to be known and P is unknown. But this is a fixed known distribution. And so now our guarantees are simply if P is equal to X except with high probability. Remember, I'm just going to say high probability is with probability 2/3, and we can do all the boosting that we have discussed before to improve the probability of success. And if, let me again just use total variation, then reject. Right? And actually, even more basic than this basic question is that X is the uniform distribution, which I'll call U. So this is the basic question that we're going to study, which just by itself is quite interesting. There is a fixed known distribution. So let's just say you could think of this as like statistical hypothesis testing. You have a hypothesis on what you think the world looks like. You are getting samples from the world, and you need to check, is your hypothesis correct? Right? And we give some slack because obviously there's going to be some statistical error in determining such a statement exactly. So all we would like to do is to distinguish, is our hypothesis good enough? This would mean that the hypothesis really does not reflect the world, right? So this is your hypothesis, this is the world. So this is statistical hypothesis testing, the most basic question. And interestingly, even in this world, which is such a classic question, we're going to prove something quite non-trivial using a non-trivial algorithm. And again, within this even I just said X is some fixed known distribution. More specifically, X could be the uniform distribution. X is a uniform distribution, which I'll denote as U over the universe. So we need to determine, is this unknown distribution, is it uniform over our support, or is it significantly far from uniform? Okay, any questions? So Ross, hopefully that clarifies, that gives you a specific example of what we're looking at.
Yeah, I was just like imagining like keys that were like really like there's lots of things that are like close to each other, but there's also lots of holes, and it seems like you really wouldn't be able to do anything in that case. But maybe you can do anything, and that's fine.
We'll see. We'll see. I mean, I'm actually going to show you that. Okay, so I will answer that shortly. But is this does this make sense?
Yeah.
Any questions? Okay, very good. So this was the distribution testing question. But let me now ask an even more basic question, which is learning a distribution, and I should technically say a categorical distribution. Okay, so again, given sample access to the input distribution P and epsilon greater than 0, output Q such that the total variation between P and Q is at most epsilon. This is the learning problem. Now note that if we can learn a distribution, then we can perform distribution testing for any property. Why? Because if you can learn, then what you can do is you can find, okay, so technically what you're using is the fact that the total variation distance satisfies the triangle inequality. Right? That is basically what we're doing. Because if you can learn a distribution, then for any P, you can actually learn something Q that is sufficiently close to P, and you know what Q is. It's an explicit description. So given Q, you can, you already, in some sense, we are only measuring the samples to the distribution. Right? So once you have Q and P, you can do whatever you want to determine whether Q lies in P. I mean, this is something where you do not need to sample, and therefore we don't charge the running time or the sample access or whatever of that. So once we get this vector and we have a description of the set, then of course we can just determine if Q lies in P or not. And if Q lies in P, we just go ahead and accept, otherwise we reject. So again, like to answer the previous question, actually, regardless of what P looks like, if you learn the distribution, regardless of what bold P looks like, if you can learn the distribution little p, then of course the testing problem just immediately follows. Going back to the basic question, this completely makes sense, right? So here's this fixed known distribution. Here's an unknown distribution. So P is the unknown distribution. So obviously, to solve this question, one can go ahead and just learn what P is up to some total variation error. and then just say that does that match the hypothesis that we have. Any questions? I'm just saying that in this case, I'm giving you examples of various questions one can ask, and in one of the questions, x is the uniform distribution. But in general, you can this question. So I'm not stating a theorem. I'm stating a question. This question makes sense for any fixed distribution. So nothing that I have said so far assumes that x is uniform. I'm just maybe I should have written this more properly. I'm saying the question of uniformity testing, or rather the problem of uniformity testing, is when x is the uniform distribution.
Sorry.
Yeah.
My question is, so the main problem here is to how many trials or how many samples we need to find such that we can test if this t belongs to a specific distribution.
Exactly. Precisely. And
Yeah. How?
mhm.
How to decide it?
So this is exactly what the whole field is about. This is exactly what the whole field is about, and what I'm going to show you is that uniformity testing can be done using a fairly non-trivial algorithm and analysis. But good. I mean, I think you stepped ahead. So this is exactly the main question, which is how many samples do you need? And so let's first start with the more basic question of learning a distribution, because if learning a distribution is extremely efficient, then one can just go ahead and learn the distribution. Why do testing? And so this leads us to a very important question, which even, keeping testing aside, is how many samples S required to learn a distribution P. Again, when I say learn, I mean learn up to total variation, up to TV of epsilon. Okay, and this is where all the balls and bins and the Chernoff bounds will tell us the answer. So draw S samples. Right? Let Q of I be the number of samples with value I divided by the total number of samples. So the vector Q is the empirical distribution. And how well does Q approximate P? So fairly simple, well to state fundamental question. I took S samples. I look at the empirical distribution. How well does the empirical distribution actually approximate the true distribution? So let me actually start with the easier but looser theorem, and then I'll give you the tighter optimal one. So the following I'm not going to prove completely. I'm just going to sketch it out and leave the details as an exercise. So let S be at least Cn log n over epsilon square. C is just some sufficiently large constant. Then, with high probability, I get the following guarantee. With high probability, for all I, so I have two guarantees. I'll say if P of I is less than epsilon divided by 3n, then Q of I is going to be at most epsilon divided by 2n. So if P of I is small, then my estimate Q of I will be small, but I'm going to be potentially off by some constant. And the second is to say, well, if P of I is greater than epsilon divided by 3 of n, then Q of I is going to be a good approximation of P of I. All right? So these are the guarantees that I give. So with high probability, before I sketch out the proof, which is basically an application of Chernoff bounds, but different regimes. Different regimes. So one has to be a little careful here. Does the theorem statement make sense? So I'm saying take n log n divided by epsilon square samples. Then we guarantee that we're essentially going to nail down all P of i's that are sufficiently large. For any P of I that is small, we cannot guarantee that we're going to approximate P of I explicitly, but our empirical estimate is also going to be sufficiently small. So one thing that is very important to note is if I do not have this assumption, I cannot get such a guarantee. Why is that? If I make no assumptions on P of I, I cannot get such a guarantee. Why?
You can have something that's arbitrarily close to zero, but not zero.
Exactly.
That you couldn't get a multiplicative bound on it.
Exactly. Like, what if P of I was tiny? Well, then there's no way one can give such a guarantee. So one has to resort to a much weaker guarantee. On the other hand, this weaker guarantee is enough to give us the total variation distance. So we can just say that in this case, or I should say, when 1 and 2 happen, now let's just go ahead and bound. Let me just, instead of the total variation, let me bound L1 distance. It's going to be more convenient. So it's just summation of P of I minus Q of I, which I will split as all I, such that P of I is greater than epsilon over 3n. So P of I minus Q of I plus all I such that P of I is less than equal to epsilon over 3n, P of I minus Q of I. And of course over here I'm given my multiplicative guarantee. So this difference, so the summation over all I such that P of I is greater than epsilon over 3n. This is at least epsilon times pi. When this is small, I know that Q of I is at most epsilon over 2n. So I could simply sum over all of these i's and just say it's epsilon over 2n. Sorry, so let me sort of make this guarantee 1 plus minus epsilon over 2. And what I get is that this is at most, this quantity is epsilon, and this quantity, this quantity is at most epsilon over 2. The second quantity is also at most epsilon over 2, which gives me epsilon, right? Because there are at most n terms here. And so when 1 and 2 happen, I'm guaranteed to have an L1 distance of at most epsilon. And the total variation distance is half of that. Okay, so this suffices to learn. This suffices to learn. Now, how do we prove this?
What was the bound on? How did you bound the first sum for the big PIs?
For this? Sorry, there
Yeah,
should be no C.
Oh, it's epsilon over 2.
Yeah, it's epsilon over 2 times P of I. Right? That's exactly what this guarantee is. This is just saying the absolute.
There might be like there's n terms though.
Oh, but yeah, but I'm just summing over all pi then. The sum of all pi is at most 1.
Yeah, right.
right? That's a distribution, right? So here I actually multiply by n, but here I don't have to multiply by n. Okay. Okay, so the yeah, sure. I'm sorry. Yes, this one. This one. Yeah, it's epsilon over 2n. Is that not clear or? Oh, I may have put it. I may have fudged up the constant. It should be epsilon over 2n, right? Because I'm bounding by qi. I cannot bound by pi. I'm just bounding by. I know that this thing is at most epsilon over 2n. Questions? Okay. So the proof is it's an exercise in Chernoff bounds. For 1, use the bound. You remember there was this bound that said probability that x is greater than r is at most 2 to the minus r when something something something. Use that bound. For 2, use the standard multiplicative Chernoff bounds. I want to emphasize that for step 1, you cannot use the multiplicative Chernoff bound. Remember, we discussed this because in the multiplicative Chernoff bound, you have a dependence on the expectation. But in situation 1, the expectation might actually be tiny, in which case you need to use this bound, which is actually agnostic to the expectation. And this holds whenever r is sufficiently large, whenever r is greater than 6 times the expectation or whatever, right? So you have this bound. So use these bounds. This is an exercise. But there is, so this part is routine. There is something that I want to mention over here. Get the error probabilities for each to be less than 1 over n squared, then union bound. Union bound over everything, right? That's the proof. Okay, then you just do a union bound. Is this clear? Any any clarifications on how to do this? It's a good exercise. But do you understand this part over here? Questions? Okay. Now you need S to be omega n log n. Ignoring the epsilons, you need the log n for the union bound to work. Sorry. You need S to be omega n log n for the union bound to work. But it turns out there's actually a stronger theorem. Stronger theorem says let S be at least Cn divided by epsilon squared without the log n. Without the log n. With high probability P minus Q total variation is at most epsilon. This is significantly stronger now, at least in terms of the asymptotics. Now, I want to emphasize this because I don't want you to think of it as, oh, I'm just shaving off a log n factor. Of course, that's what I'm doing. But there is a more fundamental point here. So when I say the number of samples is n log n over epsilon squared, then Q actually nails down the empirical probabilities, effectively nail down every single probability. In this theorem, I only guarantee the total variation. So there's a huge difference because we cannot union bound over all n. Why? Consider P being U, the uniform distribution, right? So this just means that all P of i's are 1 over n. For any I, which is really you can think of as any bin if you want to think of a balls and bins process, Chernoff will only give errors depending on whatever extra parameters you have. But that is when you set C to be C over n log n. Also, I should say maybe errors independent of n. So they are independent of n. So moreover, by our max load analysis, we know that the max load is essentially theta of log n over log n. There's some dependence on epsilon that I'm ignoring here. But in terms of the asymptotics of n, we know that the max load is log n over log n. So for this I, or this bin, the empirical estimate is incorrect or has large error. Okay, so I really want you to understand this point here. You can actually learn the distribution with n over epsilon square samples. Now there's a huge difference because you cannot carry out the previous analysis. You cannot union bound over n. So from a okay, so there are 2 points I want to make here. One is a technical roadblock, and the second is the fundamental roadblock. Now the technical roadblock is if you start applying Chernoff bound to each I, which is to each bin. You say how many balls fell into that bin. The expected number of balls is going to be some constant, or it's going to only depend on C and epsilon. It's going to be independent of n. As a result, the Chernoff bound will only give you errors independent of n, because the expectation is essentially independent of n. Moreover, the more fundamental roadblock is we know that by the max load analysis, we know that the max load is going to be something like log n over log n. So there is going to be a bin which is going to have log n over log n balls, or there's going to be some I that gets sampled log n over log n times. In the case when P is uniform, of course. Now, because it's log n over log n, the empirical probability estimate there is going to be log n over n log n, which is much more than the 1 over n. So we do not get a guarantee of this form. Remember, this guarantee said for all I. And then using the for all I, we're able to get a total variation bound. Here, we need to get a total variation bound, or the L1 bound, without being able to bound what happens for each individual bin, or each individual I. So is this point clear? Questions?
But it seems like if you're
No, the total variation, but you're going to sum over all the bins, right? So think of L1 as opposed to total variation. They're both the same. So in L1, you're going to basically sum the absolute differences amongst all the bins. So what this is saying is, this is saying that, of course the maximum is going to be off, but the average is going to be correct.
But if the maximum is off, and I guess I'm a little bit confused about if the maximum is off and the total variation depends on the maximum.
No, you mean because the total variation is written as this?
Yeah.
Yeah, but for that maximum bin, the difference, okay, so what is the difference for that maximum bin? It's log n over n log n minus 1 over n. But that's still really small. It's just that if this was the situation for many bins, then you have a problem.
But we need it to be a constant, right?
No, so here's one way of thinking of it. Let's say that each pi, let's take, instead of total variation, let's look at L1 because these are two factors of each other.
I guess I understand why the L1 difference should be small. So I guess I'm just confused about the equivalence there because log n over n log n minus 1 over n is small, but it's not a constant.
No, it is no. It's. Think of it as, what is this? Okay, so ignoring that, this is essentially just this, right? I mean, you can ignore that. So for that bin, the difference is log n over n log n, but you're going to add the differences over all the bins. I mean, this is still. I mean, there's a 1 over n over there. There's an n in the denominator, which you need to get rid of. If this was a situation for only one bin, total variation is still going to be tiny. Let's just say there was one bin where it's log n over log n, and all the other bins it was actually like constant.
Sure.
Then the total variation distance is going to be also at most some epsilon. So let me just give you a situation. So let's just say for some bin, so I'm looking at the q values here. So let's look at the q value. I'm sorry. So the q values. Okay, let's look at actually the number of balls. So there's some ball in which it's log n over log n, and in all the other balls it's exactly 1. And then maybe there are a few balls where it's 0, so that things balance out. Okay, so how many balls bins over there? That's log n over log n. Right? Then things will balance out. This is pretty much everybody. And this is one bin with log n over log n.
But when you're measuring the total variation distance, you only care about that one bit.
Yeah, but if you're going to maximize. Sure, you're going to carry about that one bin. So what is the total variation distance you're going to get? You're going to get log n over n log n. But this is much smaller than epsilon. For that one bin, there's you're dividing by n. For the total variation distance to be significantly large, you need this to happen for many bins. But this is the subtle point here. What is being said here is, by the max load analysis, we know that there is going to be some bin with large load. This analysis is implicitly going to show there cannot be too many bins with a large load. So the averages are going to behave the right way. And that's sort of why I want to emphasize this point here, which is there is a subtlety in the analysis because you cannot do the union bound. Even though you are not nailing down every single probability, you're still going to get the average to work out. Okay, any questions about this? All right. So the proof is fairly short. So let xi be the number of samples with value I. So we know that the expectation of xi is exactly s times p of I, right? And q of I is going to be xi divided by s. So we want to show that the expected value, let's just deal with the expected value, and then we can just do Markov on top of that. The expected value of the L1 distance is at most epsilon. This is what we want to show. So let me just write this out in terms of the x's. This is just saying that the absolute expectation of the sum of I going from 1 to n of p of I minus xi divided by s is at most epsilon, which is equivalent by, linearity of expectation, moving things around. This is equivalent to saying that the expectation, so the sum of I going from over the support of the expected value of, I'm just going to move things around a bit, xi minus p, might hope to write this cleanly over here. The summation of I going from 1 to n, the expected value of xi minus s pi, this is at most epsilon times s. This is what we need to show. Okay? We need to show, so now we're looking at the absolute value of this deviation. And we're taking the sum of expected absolute values of the deviation, and we're saying this has to be at most epsilon times s. Now, if you did a naive analysis, you would try to compute the maximum, and then you would bound this by n times the maximum. The max load analysis says that this is not going to work. You cannot simply try to find the largest deviation and just bound by n times the largest deviation, so you have to be somewhat more careful. So what we're going to use is we're going to use Jensens inequality. Now this is stated in many different ways. You can use it in either way. So the simplest version is that for a random variable y, the expectation of y squared is greater than the expectation of y whole square. And more generally, the version that I'm going to use here is for concave functions. You can also write the one for convex functions. If f is a concave function, then whenever I use Jensen, I always have to draw this picture to myself. What Jensen says is the following. It says if you put a line between these 2 points and you look at the value of the line, so here's f, look at any x. This is going to be less than that. This point here is less than this point here. This point is the average of f values. So this is like saying it's the expectation of f of y. And this is the value at the average is less than f of the expectation of y. I mean, you can derive this by replacing this by convex and switching the signs. I'm going to use this version here, but they're all equivalent. And I'm writing this maybe in 2 very different ways so that you can see both, and as an exercise, the Jensen calculation that I'm doing, you can do it with either. So here is the expectation that I'm interested in, xi minus spi. I'm going to simply write this as the expectation of the square root of xi minus spi squared. Square root is a concave function. Therefore, I can say this is the square root of the expected value of xi minus s pi squared. But this is an expression that I know and love. This is basically the variance of xi, which is a binomial. So I have a formula that I can plug in to deal with that analysis. Okay, this was Jensen over here. Alternately, I can look at xi minus spi as a random variable y and apply this inequality. You'll see that this is the expectation of y squared, and this is the expectation. I mean, if I'm sorry, I have to yeah, and this is the expectation of y. So one can do this either way. Okay, is that clear? So the square root with Jensen goes from inside the expectation to outside the expectation. Now this quantity here, this is just the variance of xi. Now the variance we know is exactly s times p of I times 1 minus p of I. This is s times the variance of the individual Bernoulli, which I'm just going to write as s times pi. So I can write this as the square root of s times pi. Okay, now that I have this, I can look at the L1 distance between P and Q is at most the sum of all of these quantities. So it's the sum of I of the square root of S times Pi, which is equal to the square root of S times the square root of Pi. So I get the sum of roots of probabilities, right? And this is I in N. Now I can write this as either an L1, L2 inequality or Cauchy-Schwarz. So let me just say that, let me just write this as Cauchy-Schwarz. And so by Cauchy-Schwarz I get this. So the square root S of course remains. I'll get the square root of N times the square root of the sum of P of I. But this is just 1. And so I get this is the square root of S times N. This is the square root of S times N. Is this clear? So I started with Jensen. I use Jensens inequality to get an upper bound on the expectation of x minus the absolute value of expectation of x minus SPI. By Jensen, I can write this as the square root of S times Pi. Now I sum these square roots, pull the square root S out. That's a constant. I mean that doesn't depend on I. And now I have the sum of square roots of the probabilities. By Cauchy-Schwarz, that sum of square roots is at most root n. Okay? What do I want? I want this square root of Sn to be less than epsilon times S. Right? Or let's just say, let me make that epsilon times 3s. Work the math out. So obviously if S is at least 9n divided by epsilon square, and square root Sn is going to be most divided by 3. So what this means is that the expected value of the total variation or of the L1 distance is at most epsilon s. I should probably say so I'm fudging a yeah, I should say s times this. S times this is that. So I'll get that the total variation is at most epsilon times 3. So by Markov, the probability that this is at most 3 times the expectation, is at most 3 times the expectation, or is at least 2/3. Okay? And so that completes the analysis. Any questions? So let me pause here. I'll take any questions that you have, maybe talk through whatever I've done so far, and then we'll continue with uniformity testing. All right, so now that we have this sort of fundamental theorem in place, now we can ask the distribution testing question. We now have a better sense of what we are looking for, which is in distribution testing, the main game is beat the n over epsilon square learning bound. And specifically, the first question in this form, which is, can we test if P is U in little o of n over epsilon square samples? And so a very remarkable result is the answer is a resounding yes. It can be done in O of n over square root n over epsilon square samples. This result is by Paninsky in 2008, who got this dependence, and this is optimal. The n over, like, this exact expression is optimal. This is optimal. But the first group of researchers to pose this question and answer this, it was actually Batu, Fortnow, Rubenfeld, Smith, and White in 2000, who basically showed that you can do this in root n over epsilon to the fourth samples. And this is a seminal paper, Batu et al., which first posed distribution testing. Although Goldreich and Ron, in a somewhat different context, this is actually in '99, already sort of, gave the root n over 4 analysis sort of implicitly. Of course, what Batu, Fortnow, Rubenfeld et al. They showed much more. They could show that you could do the samples for any fixed distribution. What I mean is, you can actually test if P is x for any x in root n over epsilon to the fourth samples. And again, this analysis has been subsequently improved to root n over epsilon squared in a series of work, a series of very non-trivial work. But what I would like to show, I don't think I'm going to have enough time to finish the analysis today, is to basically show you this result. And if you want to know where is the root n, it's birthday paradox. The root n. The general case meaning that you can test a general singleton distribution, right? To test if P is, yes, it turns out to be a reduction to uniformity. So, but you're right. Yes, you can get root n over epsilon to the fourth. And you can get root n over epsilon squared because you can actually reduce it to uniformity testing. So there's a reduction.
Is that only true for discrete distribution?
I mean, when things are continuous, you have to change your notions because now n is the support size. And then the support doesn't make sense. So you could potentially discretize your continuous distribution and then pose these questions, which, or you would, there's you need to sort of change the formulation. I've seen some formulations of these, um, but I think that in some sense, at some point, you basically discretize things to some granularity. Um, but the algorithm and the analysis are really, it's really beautiful. Because when you think about it, you can say, how can you actually test the distribution without learning the distribution? How can you determine that it's close to uniform without even learning it? And how can doing it for arbitrary seems even harder. But even the uniform case is quite surprising. So let me start by doing an alternate characterization of the uniform distribution. So for any distribution, let me look at the 2 norm squared. Right, and what is this? This is the summation of I and n of p of I squared. Okay, now remember we know that the L1 distance is greater than the L2 distance, and the L2 distance is greater than the L1 distance divided by root n, and this is Cauchy-Schwarz, because you can say the summation of p of I is at most the square root of n, square root of summation of p of I squared. Right, so this is Cauchy-Schwarz. Now applying that bound over here, so the L1 is just 1, and so this is at least 1 over n. Now the 2 norm squared of the uniform distribution is exactly 1 over n. So the uniform distribution minimizes the L2 norm. And this is going to be very useful for us. And now let me give you an even more interesting claim. Is let me look at the 2 norm squared between P and the uniform distribution, and this is going to be exactly the 2 norm squared minus 1 over n. And the proof, it's an exercise. Just expand out. Now this is going to be really fundamental, because we can now say, suppose the total variation distance, let's say the L1 distance, is more than epsilon. Okay. So now we know that L1 is So sorry, yeah. Let's go back to these inequalities here. L2 distance is at least L1 divided by root n. What this means is if we look at the 2 norm, this is at least the 1 norm divided by root n, which is at least epsilon divided by root n. That means that the L2 norm squared is at least epsilon squared divided by n. Let's go back to our claim here. And now let's state this as a lemma. And we'll say if the 1 norm, the total variation, the one distance is at least epsilon, then the norm of P itself is at least 1 over n plus epsilon squared over n. And if P is the uniform distribution, then of course the 2 norm squared is just 1 over n. So this gives a convenient way to distinguish a distribution that is uniform, rather to distinguish the uniform distribution from a distribution that is far from uniform. It suffices to look at the norm of the distribution, the gap that you get. So if the distance is at least epsilon, then the 2 norm squared is at least whatever you have for the uniform plus epsilon squared over n. So does this make sense? This is the crucial lemma that we're going to use, and this is an important feature of a lot of distribution testing, which is this manipulation of norms. Like you start with total variation, you look at 2 norms. In some of the analyses, you look at 3 norms, or you look at other versions of notions of distance, like other divergences. But this very simple sort of math that we did here is going to be the crux. Like this is going to give us the main indication towards how to do this better than n over epsilon squared. Questions on this? Okay. Now let's look at what this 2 norm of the distribution is. This is really the probability that 2 independent samples are identical. And now we get the birthday paradox connection. And this is birthday paradox, which is really you're trying to analyze when you're throwing balls, what is the probability that 2 balls end up in the same bin? So this is the probability that 2 samples are identical, 2 balls in the same bin. Okay. So what is the algorithm? Okay, so now we have this lemma. The algorithm idea is to estimate the 2 norm and use the lemma to determine or to distinguish u from p minus u greater than epsilon. So what we need is an algorithm that will estimate this 2 norm. The estimation, we are going to use the birthday paradox. Now let me tell you the algorithm. Choose S samples. I'm going to set S. I'll tell you how to set S shortly. Count pairwise collisions. What is a pairwise collision? Two different samples with the same value. So we're going to count pairwise collisions and call this K. And output K divided by S choose 2 as the estimate of this 2 norm squared. And then of course use the lemma. Then use lemma. I should say, instead of output, I would say basically use K divided by S choose 2 as the estimate of the 2 norm squared, and then use the lemma as above, right? So you check is what is the difference between the estimate and 1 over n, and if this difference is sufficiently large, then you reject, otherwise you accept. Okay, so maybe let me just sort of write this out then. Now we'll say that if K divided by S choose 2 minus 1 over n is, say, at least epsilon square over, we'll keep some slack there. We'll say reject, else accept. That's going to be the algorithm now. Very non-trivial, very different kind of algorithm. It doesn't really estimate individual probabilities. It's going to choose some S samples, count the number of pairwise collisions, divide that by S choose 2, subtract 1 over n, and then use that to determine whether to accept or reject. So any questions about the algorithm?
Why not just use the empirical norm?
The empirical L2 norm.
Yeah. I mean, just take a bunch of samples, make your empirical vector probabilities Q, and then take the L2 square root of L2.
So good question. What's going to happen is if you set S to be really small. So let's just say you set S to be root n. Then, or less than root n. You know that by birthday paradox, you're just going to have these root n samples go into different bins. Your empirical norm is going to be extremely high. So you have to do much more than just look at the empirical distribution. And that's the magic here. Is that the empirical distribution with S samples, so S is going to be much, much smaller than n. So your empirical distribution is going to be completely off. So you could have distributions that are far from uniform, but empirically the distribution might look, empirically with so few samples, things might look uniform. Just to give you, some sense of the challenges here. So here's the uniform distribution versus distribution uniform on n over 2 elements and 0 elsewhere. Right? This is far from uniform. This is far from U. And if you think about it, you need to take a large number of samples to be able to learn this distribution explicitly. On the other hand, it turns out that the collision probabilities, which is the probability the birthday paradox calculations, will be able to distinguish between these distributions in far fewer samples than actually learning the explicit distribution. Asymptotically, of course. Okay? So let me sort of write down the sort of the crux of the analysis. So I'll say choose S to be C root n over delta square sample. So I'm using delta. I don't want to use epsilon. And then let my random variable x be equal to the number of pairwise collisions divided by k choose 2. So it turns out that the probability, I'll get the sort of typical deviation bound. So sorry, let me first look at this random variable. What is the expectation of x? So let's look at the expected number of pairwise collisions divided by s choose 2. So let me just take the numerator. So I'm going to use A and B to index samples. So I'll say A not equal to B. I should just say A less than B of, this is the expectation of the Ath and Bth sample colliding. Right? I'm just breaking up the number of pairwise collisions into the individual pairs. This is now going to be the summation of 1 less than A, strictly less than B, less than S of the expected value. This is linearity of expectation, Ath, Bth sample colliding. The value of this expectation is precisely P of I square, which is the 2 norm squared. And so this gives me exactly S choose 2 times the 2 norm squared. Plugging this back in, I know that the expectation is exactly the 2 norm squared. And so now I can go in and say the probability that x does not lie in 1 plus minus of delta of the 2 norm squared is at most 1/3. And so this is now going to be the main theorem. If I choose S being C root n over delta square samples, then I get a 1 plus minus delta estimate of the 2 norm, with high probability. And going back to this analysis here, I'm going to set delta to be epsilon square so that I can get the desired accuracy. I'm going to set delta to be epsilon square. And in general, what I will do is, so I have this done, I will set delta to epsilon square to estimate the 2 norm squared to the desired accuracy. This theorem here is the main birthday paradox calculation that I need to show you. And this analysis is where we'll get the root n from. The epsilon to the fourth we get because we have a delta squared to estimate the 2 norm squared, or the 2 norm up to 1 plus minus delta accuracy. And the delta that we need to set is epsilon squared, and that's what we get from the previous analysis, right? From the lemma that we used, where we relate the total variation. The total variation was related to the 2 norm squared, and that there was an epsilon square over there. So that is the accuracy that you need on measurement of the norm. And what the birthday paradox calculation says is, well, you pay quadratic in that accuracy, which is sort of the typical thing that we see in a lot of these situations. And so we get epsilon to the fourth. And you need a more sophisticated analysis to get rid of the epsilon to the fourth. You cannot go via this route. But that is something that I probably will not cover. So I think I will end here. So in the next lecture, I will do the full analysis of this theorem, and then maybe talk about more aspects of distribution testing. So I'll stop here and I'll take any questions that you have.